Okay, so here we're going to be talking about the graphs of polar equations, and these are called the classical curves. Okay, the first one is going to be the circle, which we talked about in a previous lesson. And the circle is just easily represented instead of as x squared plus y squared equals the radius squared. It's just represented as r equals cosine of theta or r equals sine of theta. Okay, and I'll show you the difference between those in a sec. Now here's a certain type of letter. This is a limacon. Okay, and it should have a little curly Q at the bottom because it is French-ish. So let me try to draw a little bit of a curve. There you go. So it's a limacon. I don't know the alt code for that letter of C, but it is just basically a number minus another number times cosine of theta, and A has to be less than B or A has to be greater than B to be a certain type of limacon. Okay, so there's different types right there. Okay, now cardioid is what happens when both those numbers are the same and we're adding. Okay, so difference between limacon and a cardioid is going to be a plus and a minus, and cardioid is both numbers are going to be the same. Okay, a lemniscate is what happens if I square the r and then square the number being multiplied by it and do the double angle right here. So that's a lemniscate. And a rose is a really pretty graph, and it's what happens if I take a regular circle and times it by a number in front and then times theta by a number as well. Okay, now there's some formulas in here. 2b petals, so it's an even amount of petals if b is even. It's the regular number of petals if b is odd. Okay, and here's a spiral of Archimedes. So this one's really kind of cool around here too. So this is just a times theta. So this is just as if we took the cosine and sine out of it and just multiplied theta by a number. Okay, now cosine graphs are along the x-axis, so they'll be restricted to the x-axis, and sine graphs align with the y-axis. Okay, now these are going to be pretty complicated, and you'll learn later if you had to transfer these back to rectangular equations. So polar equations are infinitely more complex if we had to change them back to regular plain old rectangular stuff. Okay, so here we go. Alright, so here is circular equations about the origin. Okay, so this one's actually just r equals. Okay, and as you can see, that's infinitely more easy than just dealing with the actual graph of x squared plus y squared equals radius squared. So r equals is just there. Okay, now circular equations about other parts is going to look like this. So there's the example. The difference between the sines being along the y-axis and the cosines being along the x-axis. Okay, now let me scroll down to where we get a. There we go. Okay, so if we make a bigger, obviously the graph grows bigger. Now if we make them negative, they go in the other direction. Okay, so let's go back to 1. Okay, so those are the circle equations right there. Okay, now here's another way to also represent limacon equations. Okay, limacon equations are when a divided by b absolute value is greater than 1 or less than 1, and that's just representing the plus or minus. Okay. Alright, and cardioids are when a and b are equal. So when I graph these, you're going to see a cardioid first because a and b are equal, because I set a and b equal to 1. Okay, and then if I do the same thing here, I got the pluses. So the pluses are going to look like this right here. The minuses are going to be going the opposite direction. So these are the minus ones. Okay. Alright, so let's take a look at the pluses first. Okay, so these are cardioids. Now, right now, A is 1 and B is 1. So if I match up A and B, they should be there. But if I change A to be bigger, I get a limacon. Okay. So the difference is just the A is bigger, or the number being times by sine is bigger. Okay. Now if I make it smaller, it's going to be a lemniscate that's going to be a little bit more interesting. And if you see, if I just make it 0, it's going to turn into that circle about the origin. Okay. And as you can see, as I make it bigger, it's going to be like that. Now, same thing as if I do it right here or here. As you can see, it's just basically a reflection of each other. It's really cool how you can make some of this stuff sometimes. Okay. All right, now if I make b back equal to it, we get our cardioid. Okay, but if I make it bigger, now if you notice the cardioid, it makes a heart shape, and the heart shape is going to touch the little I guess you could call that a butt-like shape, touches the pole. Okay, so that's a cardioid. But if I make it bigger, if I make b bigger, the butt part doesn't touch it, and it becomes a limestone again. Okay, so this is a limestone, and this shape where it goes inside is a limestone as well. Okay, so there's the differences between those two types of graphs. Okay, and as you can see, I can do the same thing when I do the pluses and the minuses. Okay, and that's some really cool stuff that you can work with right there. Now we're going to go on to a rows. Now rows, okay, we're going to change, as you can see, I have a slider for n as well, and that's going to give me the actual number of petals. So rows right here, this is an n equals 1. If I make it n equals 2, as you can see, if I make it a really funky number, it's going to look really weird. But if I make it a nice whole integer, it's going to be 2. There's actually 4 petals. Okay, and if you remember, the rule for roses is if you have an even amount of this number, it's going to be n times 2 the amount of petals. Now if I did if you notice, it's cosine, so it's aligned along the x-axis. Okay, and it's going to be symmetrical with either the x or y axis. Okay, now sine is going to be symmetrical the same type of way, except they're not going to be on the axes. So that's a really interesting quality of them as well. Okay, now I'm going to go ahead and make this 3. Okay, and as you can see, the decimal parts I get are going to be kind of funky. Okay, now this is where the two separate themselves. Okay, so cosine is going to be symmetrical with the x-axis, okay, and sine is going to be symmetrical with the y-axis. All right, so those are the two parts. But as you can see, I have 3 as my number, and so therefore I have 3 petals because it's odd. Okay, so it's some really cool stuff when working with it. Okay, now lemniscate I can represent as r squared. I just decided to represent it as this part right here. Okay. Alright, so if I increase the size of C in there, it's definitely going to look like it's an old infinity symbol. This one as well. Okay. Does anything else change about it? Well, if I change A, it just changes the size as well. It's not going to change as much as C does, but it definitely does have a cool property of looking like an infinity sign. And then good old spiral of Archimedes. And let's put an A in there. So A times. Okay, so if I change A, I can change the size of it. So it looks really kind of cool. So I could get down to a really small number, -0.1. Let's go back to 0.1. Okay, all right, so the smaller A is, the more it's going to go. Now technically this should go on forever, but this one's just stopping it right here. Okay, all right. Now that's the examples of the actual things and how you work with them. Just keep these rules close by when you're working with classical curves of graphs of polar equations. Now, like I said, they look like they're pretty easy in polar form, but trust me, later on when we learn how to convert from polar equations to rectangular equations, they become infinitely more complex. So these ones are very nice indeed. Okay, all right, that's it for classical curves and graphs of polar equations. I will talk to you guys later. Bye.